Today we're going to be talking about the graphs, functions, the Cartesian plane, and inequalities. So I'm going to be going over the behavior of functions, different types of functions, and I'm going to be focusing on manipulating and reading them. I'm also going to be covering systems of equations and how intersecting points between two or more graphs can be found. So let's start with a quick review. In grade 10, you should have learned that functions are essentially a series of operations done to an input to obtain an output. Think of it as a factory. Raw materials, or your X, go in, and according to what type of raw materials go in, different outputs come out, which is your Y. The function itself is the factory, and different functions do different things to the same input. Another way to think about this is your X coordinate, or the place on the horizontal axis, marks the location horizontally. The function then shoots up from the point to a height predetermined by the function. So the function is going to, the machine or the function itself is going to determine how high each point goes. And how high it goes is dependent on what X value you're at. So a rule of functions is that for every X value, there is only one corresponding Y value. However, multiple X values can all correspond to the same Y value. So basically this just means that in a function, you're never going to have 2 points directly on top of each other, but you can have 2 points at the same height next to each other. To test whether something is a function, we can use what is called the straight line test, which is literally just seeing if there is a point on the graph where the line is directly above itself. If the line is directly above itself, that means there is 1 point X, so 1 point on the horizontal line, that corresponds to 2 points Y. And that means that it cannot be a function, because a function is literally defined by 1x is going to spit out a y. It's not going to spit out 2 y's, and not going to spit out 3 y's. It's going to spit out 1 y. So let's just say when you have a function, y is equal to x, right? This just means that your input's going to be your x, your output's going to be your y, and f is going to do something funny to the x. So you could also have, let's just say y equals fx equals 2x plus 3, or fx equals 2x plus 3. What that means is for every change in your input, you're going to be changing the x in the equation. So let's just say we're going to stuff in 1. What's f going to do to the 1? Well, we can see that in our 2x plus 3. This is basically what f does to the input. So if we have f of 1, we can simply just replace the x inside the expanded expression or whatever the actual function is. Just replace all the x's with 1, because x is equal to 1. So we're testing to see what the output is at x equals 1. So that's just going to be 2 plus 3, which is equal to 5. Let's try f2. That's just going to be equal to 2 times 2 plus 3 equals 7. f of 3, so on. 2 times 3 plus 3 equals 10. Notice how the 3 doesn't change because it doesn't have an x term attached to it. The x term is the only thing that changes if you change the x term. Yeah, so stuff like f of f3, right? This can be read as fx when x is 3. And since fx is equal to y, fx equals y, f3 is also equal to y when x is 3. And you can also read it like that. F of 3 is equal to y when x is 3. Similarly, when you have a function x is equal to f of y, well, great. Now you just switched your input and your output. To find f of 3, assuming that, x is still f of y, and y is 3 now, you can just simply replace every y in there with a 3. So let's just say we have 2y plus 3. X is equal to 2y plus 3. X is equal to f of 3 is equal to 2 times 3 plus 3 equals 9. There you go. There's your x. Now let's talk about zeros, or solutions to the equation. So zeros are when the function intersects the y-axis. And the reason they're called zeros is because since the y-axis is at y equals 0, to touch the y-axis, the function will also have to be equal to 0 at some point. Not all functions have zeros, but it's quite simple to test whether they will or not. Simply set the entire function equal to 0, as you're only really setting the y-coordinate to 0 in this case, and solve for the x-coordinates that will make the statement true. If there are no x-coordinates that will make the statement true, you'll be able to see that while you're trying to solve for it. So for example here, I have a function y equals fx equals 3x plus 2. We're simply going to set the function equal to 0. So y equals fx equals 3x plus 2. Simply set the function equal to 0. 0 equals fx equals 3x plus 2. We're going to isolate our x. And solved. Done. So if we want to plug this x value back into the equation, we're going to see that 0 equals 3 times negative 2 over 3 plus 2. Is this equation true? Let's see. It is true. And done. If the equation is true and your x value, when plugged back into the equation, yields a true equation, or in this case 0 equals 0, you've solved for a root of x, or a solution for x. Similarly, if we had a quadratic expression, let's just say f of x is equal to x squared plus 3x minus 28. So first of all, we're going to set fx to 0. 0 equals x squared plus 3x minus 28. Now, on inspection, we can't really tell what x values are going to make this statement true. What we could do is we could factor it to simplify the equation. So if we factor this thing into its polynomial factors, which would be, I think, x plus 4, no, it'll be x plus 7 times x minus 4, because 7 times negative 4 is negative 28, and 7 minus 4 is 3. We get, to make this equation true, x must be equal to negative 7, as negative 7 plus 7 is 0, and x must be equal to 4, as 4 minus 4 is 0. Notice that we're not actually looking for the constant term. We're looking for the value of x that would interact with a constant term to make one of these things 0 times an x plus c term in another, or x plus c times 0. All right, back to this. Here are our solutions. If we wanted to plug them in, I'm not going to do that here to save time, but if we wanted to plug them in to test, this equation would turn out to be true. So what we've essentially done is we've taken, let's just say a graph, right? Let's take our first graph, 3x plus 2. We've taken a graph, and we've basically just put into our equation, right here, we're going to have a point x, y, but we know that the y is going to be 0. So, since we know the y is going to be 0, we can set the entire function equal to 0. And you can see visually at this point that since this line is 0, this line must have a y-coordinate of 0. So those were zeros, or x-intercepts. There are also y-intercepts, where to touch it, x must be equal to 0 instead of y being equal to 0. So let's take a look at this. Y-intercepts. To find your y-intercepts, notice how the y-axis is located at x equals 0. So simply set x to 0. Let's just take a previous example, 3x plus 2. If we want to find our y-intercept, we know that it's going to be here. But what are the coordinates of here? Well, we know that the y-axis is going to be located at x equals 0. So we know that the first coordinate is 0. And we know that the second coordinate is, y. And now it's just a matter of solving for y. How do we do this? We're going to plug it back into our formula. So f of x is 3x plus 2. Now let's plug in a 0. F of 0 is equal to 0 plus 2 is equal to 2. And boom, there you have your f of x, or in this case, f of 0 is equal to y is equal to 2. And now you've solved for your set of points, 0, 2. When x is 0, y is 2. Now, that was fairly simple. Those were zeros and intercepts, so places where the functions touch the axes of a graph. Note to self, zeros are often times called solutions when there are no secondary functions involved. Now we're going to talk about something a little bit harder, a little bit more interesting. So these are solutions, or points of intersection between multiple functions. Essentially, if we have two graphs on the same grid, we're asking where will they touch? So first we're going to need to establish one truth. If a graph is to touch another graph, there must be one point where both the graphs take up the same space. In other words, the graphs both exist at the same time, their x-coordinates are equal, and their y-coordinates are equal since they're in the same space. That x-y coordinate, they're both in it. So let's just say we have a function f of x touches gx. We know that there's going to be an x, y, where fx equals y and gx equals y. We feed the same input into both functions and we get the same output because, again, they exist in the same space. Therefore, at the intersecting point, fx equals y, gx equals y. Since they're the same thing, let's write a three-way equal sign. Fx equals y equals gx. Now get rid of the y, we have fx equals gx. These two functions are equal to each other at the exact same point. You see what we've done here? We've basically just set up an equation that assumes that both functions exist at the same point. Even though we don't really know exactly where that point is. We know that the fx and gx are one and the same here. And therefore, we can use this to solve for our x-coordinate. So, do they touch? Let's assume they do. And fx equals x squared plus 3x minus 7. Gx equals x plus 1. We're going to set them equal to each other. X squared plus 3x minus 7 equals x plus 1. And we're going to just test to see if there are value x that satisfies this assumption. So we're testing to see if fx touches gx and how many times. So first things first, we're going to need to factor the quadratic expression. I just shifted this side over using addition and subtraction. So in this case, this is going to break into the factors of x plus 4 and x minus 2 equals 0. So we know that to make this statement true, x must be 2 and x must be negative 4. And since this statement was just derived using algebraic manipulation from our previous statement, fx equals gx, what we've essentially done here is we've just solved the x values that satisfy fx equals gx. You can plug that in and test it. So let's just do that right now. 4 plus x minus 7 is equal to 2 plus 1, because fx on this side, gx on this side, 3 equals 3. That's true. Plug the other one in as well. I'm not going to do that just to save time. Again, in essence, what we just did is this. We knew that since both functions touch at one point, both functions would share an x-coordinate and a y-coordinate. which would be either fx or gx. Since they're the same thing, we set them equal to each other, and then we solved for x, which then yielded every possible value where this statement, fx equals gx, is true. And that is how we determine the solutions for a system of equations.